So how do you safely test the very heart of our future energy grids? The next generation power electronics that literally everything will depend on? Well, that's the critical challenge we're diving into today. And the answer, it turns out, lies in this incredible system. A really powerful tool that was born from a collaborative European effort to completely change the game in validation technology.
You see, anyone who's innovating in the power sector faces this fundamental dilemma. You've got to test your new hardware under realistic, often extreme conditions. But you can't just hook up unproven technology to a live grid. That's just asking for trouble. This huge gap, this chasm between the need for realism and the absolute demand for safety is what we call the reality gap.
On one hand, you've got pure software simulation. Sure, it's perfectly safe, but it's a totally sterile environment. It just can't capture the messy, unpredictable realities of things like thermal stress or physical hardware latency. Then, on the other extreme, you have direct grid testing, plugging your prototype straight into the power lines. It's as real as it gets, for sure, but it's dangerously inflexible and carries an immense risk of, well, catastrophic failure. So here's the bottom line. Neither of these methods is good enough for validating the complex, high-power converters that are absolutely essential for our energy transition.
So how do we fix this? How do we bridge that gap? Well, the solution is a really innovative approach known as the VEET paradigm. It uses a technique called Power Hardware in the Loop, or P-HIL for short. You can think of it as the ultimate bridge between the purely digital world and the undeniably physical one.
And here's how this elegant solution works. It's a closed-loop system. A powerful real-time simulator creates a perfect digital twin of the electrical grid. It sends out these precise mathematical instructions to a power amplifier. That amplifier takes those digital commands and turns them into real physical power to test the actual hardware. Then, and this is the key, the hardware's response is instantly measured and fed right back into the simulator, closing the loop. It's safe, it's deterministic, and it's incredibly powerful.
All right, let's peel back the layers and look inside the custom P-HIL system that was built for the Polytechnic University of Bari. Now, this isn't just another machine. It's really a testament to what's possible when you combine Italian engineering excellence with leading French and German technology. It's a truly unified European solution.
The system's architecture is built around 5 core modules. First, you've got the real-time simulator. Let's call that the cognitive center. Then there's the power amplifier, which is the system's dynamic muscle. For protection, you have the grid interface, which acts as the safety gate, followed by the output stage and the custom housing, which keeps the operator safe.
Everything starts with the brain. This is the intelligent heart of the whole operation. It's where an infinitely configurable virtual world, that digital twin of the grid we talked about, is born, microsecond by microsecond. So how does it do it? The Opal RT simulator combines a beefy multi-core CPU, which runs the main grid models, with a specialized FPGA hardware solver. And the result? You get this incredibly fast and detailed electrical simulation, with critical calculations happening in under 200 nanoseconds. That's the kind of mind-boggling, ultra-low latency you need to perfectly capture the lightning-fast behavior of modern power electronics. Okay, so from the brain's commands, we move on to the muscle. The dynamic muscle of the system is the power amplifier. Its job is to translate the simulator's precise, low-voltage signals into high-power physical reality. And believe me, this system has some serious strength. We're talking about 30 kilovolt amps of peak power. That lets you do full power testing of real industrial-scale hardware, not just some scaled-down lab model. This is the real deal.
But it's not just about raw power, right? It's also about agility. A slew rate of over 52 volts per microsecond means the amplifier can replicate the extremely fast voltage swings of a severe grid event, like a short circuit, with absolute perfect fidelity.
And that speed is matched by incredible precision. A wide bandwidth up to 30 kilohertz means the system can inject high-frequency noise and all those harmonic distortions. This allows researchers to stress test equipment against the kind of dirty power you actually find on real-world grids.
So how do you get the brain and the muscle to communicate instantly, without any delay or distortion? This is a really key innovation. Instead of a traditional analog connection, which always introduces noise, this system uses a direct digital-to-digital Aurora optical link. This fiber optic connection guarantees there is zero loss in translation. You get absolute mathematical stability between the simulation and the physical hardware. It's perfect.
This idea really gets to the heart of the project's entire philosophy. It's all about achieving that perfect union, the limitless, reconfigurable world of mathematical simulation, combined with the undeniable, unforgiving truths of full-power physical hardware.
Okay, so what does this union of digital and physical actually let you do? Well, it unlocks the ability to test scenarios that were once just considered way too dangerous, or frankly, just impossible to replicate in a lab.
You can emulate dynamic faults like voltage sags and phase loss instantly, and you can do it over and over again. You can perform really tough power quality stress testing. You can directly integrate and validate brand new control algorithms on real hardware. And maybe most powerfully, you can do what's called safe boundary testing, pushing hardware all the way to its destructive limits in a controlled, isolated environment to find its true breaking point without any real-world risk.
You know, this system is so much more than just a piece of advanced equipment. It's really a cornerstone for a future that's built on European partnership. It's a shared asset, engineered from the ground up to accelerate innovation and strengthen the continent's scientific and industrial leadership on a global scale.
And honestly, these specs tell the story of its technical authority. I mean, from the sub-200 nanosecond latency of the digital core to the 30 kVA peak power output and that secure, high-speed optical data link. Every single component has been integrated to deliver totally uncompromising performance and safety.
And here it is, the result of all that work. This is not a concept or some future plan. The Polytechnic custom P-HIL system is fully operational. It's a ready and available platform for the entire global scientific community right now. This is Italian technological excellence, providing a critical tool to build the future of energy.
Which brings us to the final and most crucial question. Building the resilient and sustainable grid of the future depends completely on our ability to validate the technologies that are going to power it. The answer is going to require vision, collaboration, and powerful new tools. And this achievement, born of a united European effort, proves that we are absolutely on the right track.